So the plan is like this that we will look at some of the questions which there is some problem, and then maybe I'll try to solve it, and then we'll see whether what is it. And any wrong question or any mistake and all is there. Once there is one in the form, in the Google form, there's the last one option where you can give some comment or something. There you mention that so and so question number 7, question number 9, or whatever has some problem. Then I'll be able to look at it later. And then if the question is found to be wrong, then I will remove it from evaluation, or I will say everybody gets correct for that question number. Anyway, so which is the question number? Okay, so see, this subject, like there is a first machine is there. Okay, the DC machine. Then we will say construction, a working principle of the machine. Then there are different types: shunt generator, series generator, compound generator. All these different types. So, but then when we look at like this directly, question number 4 somewhere, it will keep on jumping between the topics. So that is what I want you to adjust to it. So it's not like we are going in a sequential way. So we'll just quickly jump between the topics. And for any question, it helps if you start drawing with the circuit diagram. Okay. So let's do that. Yeah. So we are looking at question 4. Okay, I think in the same. Okay, so let's start here. DC shunt motor. Okay, so we'll draw the diagram of it. So motor, right? So I'll keep a circle and M, and it is shunt. So the shunt field winding is here. So you're able to see it properly, right? Yeah. So now because it is a motor, the input is electrical. So there is a voltage source connected here. Can you help me with the data of the question? So what is the voltage here? So 560 volts is the supply voltage, and what is the current mentioned here? 5 amperes. And what is the other data? Okay, so here I will create the armature resistance 0.75 ohms. So 110 ohms. Okay. What else is asked in the question? Okay. Okay. So efficiency running as generator. What else? Delivering. What else? Okay. What else? Anything else is given? Okay, I'll come back to it. See, again, the same machine can be utilized as a motor and also as a generator. Depends on whether your input is electrical or input is mechanical. Okay. In this case, right now, the input is electrical for the first one, the motor. Okay. So 5 amperes. So here I can calculate this current. Okay, so what would that current be? So 560 divided by 110. Okay, so 560 divided by 110, voltage divided by resistance is the current. So oh, okay. So 560 divided by 110. So here itself is the error. Okay, so this can't be more than. Okay, so here is where the error is coming. So the error has come because of the choice of the parameters. Okay. So now at this stage, so obviously we cannot see the same. What might happen is some other student might have received a different value, and for that it is possible to solve the problem. But anyway, because this thing has come, so we will try to uh, discard this question. Yes, but we will solve it. Yeah. Okay. Okay, so let's do one thing then. I will go with the correct values and then we will see. The same question with the different values. Okay. So, yeah, go ahead. So, what are the values? 290 volts, 5 amperes, 0 0.4 seems to be high. Yeah. 140. Okay. Okay, so this is 290. Okay, so let's continue. So in this case, the current is 290 divided by 140. So 2.07 amperes. So this is the current here. So total current is 5 amperes. So the remaining current goes here. Luckily, we are doing DC circuits. So no need to do the subtraction in complex. So simply 5 minus this one. So 2.93. I will just round it off. So here the current is 2.93 amperes. Okay, so going downwards. Okay. Now the voltage drop can be found, and then the voltage of the motor can be found. Okay, so let's try to do that. But will that really help here? Let's look at the question once. So this is important here. It is given no load. Okay, that is what I was trying to find. So when it is running as motor, it has no load. Okay, so all the input, all the input power is going into losses. So let's mention that. So here the output is zero. Okay, so P output is zero. Okay. So now, but then the motor will still rotate. Okay, so it's not that. See, the what is the power? This is torque into omega. So omega will be there, but torque will be zero. So the output power will be zero. But anyway, the motor will rotate. Okay, so now here what needs to be found is something like this. So what is the electrical input? P in is 290 into 5, which is 290 into 5. So 1450 watts. Next, copper loss. Okay. So PCU, let's call it. So the copper loss will be 2.93 square into 0.4. So this is armature current square multiplied by resistance plus 2.07 square into 140. So this is the total copper loss. Okay. So How much is that? Can someone calculate it and let me know so that even I will verify with how much you are getting? 603.32. So I'll ignore that. So 603 watts. Okay. So the question is, I'm sending the input power of 1450. Okay, and the copper loss is taking I square R is taking 603. So what happened to the remaining? Okay, so so there's two things: iron plus friction and mechanical losses. So 1450 minus 603. Okay, so how much is that? 840. Okay, so 847 watts. Okay, so from the motor operation, this is the calculation that we got. Next, the same machine is now working like a generator. Okay. So let's make that drawing next. So we are in page number 9. So now I'll draw the DC shunt generator. Okay. So how does the generator looks like? The construction wise it is same. Here we write G to indicate it is a generator, and the load is electrical load. So some load resistance is there. This was 110, 140 if I remember, and this was point 0.4. And what is the new data given? That so the output voltage is 290 volts plus minus, and this current is 5 amperes, right? Oh, 40, sorry. So when delivering 40 amperes, so what is the output power? So 290 into 40. Okay, so that is how much? 0, 0, 9 4 36, 11, 11 here we get. So yeah, 11,600 watts. So that is the output power. Now, what will be the losses? So we were told that this output voltage is 290, right? So here also 290 it will be the same voltage, and therefore the current here it will be downwards. So the what will be the current? So 290 divided by 140. Okay, so 2 point something will be right because 14 twos is 28, right? Oh, so I think it was the same as before. And what will be this current? So here is where it is slightly different. So 42.07. Okay, so 42.07. Because it is a generator, it has to generate this much current, which goes 2 goes left side and 40 goes right side, and then it goes to the load. Okay. So now the copper loss we can find out. Okay, so what is the copper loss? 2.07 square multiplied by 140 plus 42.07 square multiplied by zero point 0.4. Okay, so again, you need to help me with this. How much is coming? Okay, 1308 watts. So let's verify that. So if this was 40, then this will be 1600. 40% of 1600 will be somewhat 640. And this one 4 square will be, this will be 4, 2 square. 4 into 14, 560. So yeah, around 11 to 1200. Okay, because 2 is there. Okay, I think this looks correct. Now what about the iron losses plus mechanical losses? So we assumed that whatever was the losses earlier in the mechanical losses, friction losses, whatever, is same. So in that case, what we got earlier, it was 857, right? Sorry, 847. So now, if I add these two, okay, so the losses, if I add, okay, so 7 plus 8 is 15, 5, and this is, I'm sorry, 8, 21. Is it correct? Yeah. So 2155 watts is the total losses. Okay. So I have output, I have losses. Okay. So efficiency is what? Efficiency as a generator is output divided by output plus losses. Okay. So anyway, it is same output divided by input. So sorry. So 11600 divided by 2155. Okay. Plus 1160. I just changed the order. So this will be the efficiency. 11,600 plus 2155. So this will be inverse multiplied by. So I'm getting 84.33 if I convert to percentage. Okay. So this is not matching anywhere. You also got 84.33. Okay.
Sir, in
So
mine, the values are different. I got the answer as 64%, and the options have like 64.7 and 64.9. I'm facing
okay.
the same
Okay.
problem.
Okay.
We all have problem in this
Yeah.
one.
Sir, to find beta, we are dividing output power by output plus loss.
Yes.
But, sir, output plus loss is not the total power generated, right? V across the generator into I is the total power generated.
Huh. So what do you say? What is the total power generated?
VI across the generator.
So total output power is that one, 290 into 40. That is the total electrical output.
That's output, sir. But the power generated by the generator is the voltage across the generator into current through the generator, right? VI.
So
But that's giving a different answer.
okay, so good. So it's a good question. So let me make a diagram to explain that question. I think it's called some power stages, something like that. Okay, so this is the diagram. So this is the P output. Okay, and this is the P input, and this is the P generated. Okay. So if you're talking about DC generator, so here we got 11,600 watts. Okay. Now, what is the input? The input is 11,600 plus what was that? 2155. It's 2155, right? 13755. Okay. So this is mechanical in nature. So this is mechanical. Okay. And this is electrical. Let's see if I make it more colorful. So in between mechanical to electrical, there is a conversion going on. Okay. So what is the value of this? Okay. So if I go back, now I'm interested in finding out EG. Okay. EG is called EMF generated. Okay. So what is the EMF generated? So 290 is the terminal voltage, which is coming at the output terminals. Whereas there is a voltage drop here, 42 into zero point 0.4. Okay. So what is a 42 into zero point 0.4?
16.8.
16.8 volts. Okay. So this voltage also might have been generated here, 16.8 volts dropping in this resistance, and the output voltage coming to 290. So I will write EG 290 plus 16.8, right? So 306, 306.8 volts. And the armature current, what is the armature current? 42.07 amperes. Okay. So if you really look at only the armature, only the what you call the rotor of the machine, it is actually generating more voltage and also more current than what is coming outside. So this is 290 volts multiplied by 40 amperes. Okay, so this is what is the electrical output. So what is this quantity? This should come between these two.
Yes, sir. 12,900.
How much it's coming? 12,909
909.
watts. Okay, so the input mechanical power is gradually being converted into some electrical, again in that again going out. Okay, now what is the difference between these two? Can you find the difference between these two?
So that would be iron losses.
Let's verify. It has to be that way. uh, let's see. If not, I will tell. I mean, we can further divide this. So what is the difference between these two? 846. So okay, so this is coming to 847. I'll round it off to 847 watts. Okay, so this is what we assume to be safe. Now if I go towards the right side, I can always make a division here. So think of it like a traffic flow, and here it divides into two parts. So now, by the way, what is this difference? What is the difference between?
1,300.
So this one is 1309 watts, and this 1309 watts, if you remember, is this one 1308 or whatever. Okay, that is the addition of copper loss of both. Okay, now this term and this term, if you notice, so this term 140 is a constant and 2.07 is also a constant, provided that you maintain this voltage at 290 volts. If I maintain the output voltage at 290, then this is also constant. Okay. So I can split these two, addition is there, right? So if I take only this 2.07 square into 140, how much is that? uh, this term 2.07 square into 140, how much is this?
Nearly 600.
Okay, so let's make it 600. So the other will be subtraction, right? So 709. Okay. Now, there is the thing is this 40 amperes. Okay, that 40 amperes is decided by the load. Okay, so for example, if I go back to this, whatever this resistance is there here, so this resistance determines how much current should be. Okay? And when this resistance, what is this resistance basically? This is the changing load. Okay? So let's say if I enter and then switch on the light, okay, then this resistance will change. Okay, so again, one more person enters, switch on the fan. One more person enters, switch on the AC. So the more you change this resistance, the more current you start taking. Provided that the job of the generator is to maintain 290 volts at the output terminals. So now when this changes, let's say instead of 40, it becomes 47 or 48. Okay, 8 amperes extra I'm taking. Will that make any change here? So it will not make any change here because this part is anyway shunt field winding, it is constant. Okay. So in that sense, this one we call it as a constant loss, and this one we call it as a variable loss. Meanwhile, this mechanical and friction losses also considered as constant. So why this mechanical friction loss considered as constant is the operating speed is more or less same. Strictly speaking, actually speed will reduce. Okay. So the speed, what is the speed function of? Speed is function of the EMF generated. Okay. In order to generate more EMF, you need to actually go more faster. But for the time being, we'll assume that to be constant. Okay. So if we add these two, then it becomes the constant losses, and whereas this one is the variable losses. Okay, and this is the total output. Now, when you get the maximum efficiency is when the constant loss is equal to variable losses, we get the maximum efficiency. Okay. So, if I increase this current, the efficiency will increase actually because if I increase this current, this term will increase. This term can increase. See, 8 plus 6 is 14, right? 1447. Adding these two. Okay. So, this total is 1447. So, I'll just add these two. So as long as this one is also 1447, the efficiency will increase. After that, the efficiency will start decreasing. Okay, um, so this whole diagram, okay, is for a generator where the input is mechanical and output is electrical. So let's draw the same diagram for a motor. So we can keep the what you call side same. This one is still electrical, and this one is mechanical. But if it has to be a motor, then this has to be the output and this has to be the input. So then here also we call it P generated, but not like this. The value will be back EMF multiplied by armature EB into IA. Okay, so back EMF multiplied by armature resistance. So in this case, let's say this is 12,000, and here the copper losses maybe 6,770 something like this. So then the remaining what is that 11,330 something will be here, and then the mechanical losses will go, and then finally the output will be coming here. So something like that. So depending on the question, you need to do that. Okay, so
So I have another type of doubt, sir.
yeah,
Sir, 200
go ahead.
volt series motor has an armature resistance of 0.
So you're talking about a new question.
Yes, sir.
So yeah, so before we close this question, I think so. The point is for even if the data is correct, in the end
Answer is
the
matching.
answers are not matching. So we will ignore this question. So the same question is repeating somewhere, right? So,
Yes.
but the thing is, some students might not even receive this question. So because not only the numericals, I am also changing the question model also. So some people might not even receive this question, so it is fine. So then there's no problem. I'll try to find who all received this question, and then I'll do that.
I'm facing the same problem with 3 to 4 questions.
Okay.
That options are not matching.
Okay. Okay. So, so 11:37 time. Okay. So we have more. How much?
20 minutes.
20, 15 minutes maybe. So let's see. Let's take one or two more questions, and then the remaining also we will do. So shall I come out of this paper? Okay. So
So, just one small doubt. What do you mean by rotational loss? Copper loss, iron loss, mechanical loss.
yeah.
What is the meaning of rotational loss of a machine?
Okay. So
Is it
it's
question
not in this question, right?
question 3 in the previous?
Huh,
What
huh.
is the meaning of rotational loss?
So rotational loss mainly means the mechanical loss. So when it is rotating because of the friction in the middle one, that is one loss. And sometimes we include the iron loss also. Okay. So what is iron loss in a DC machine? By the way, this is again a kind of interview question. What is iron loss in a DC machine?
So that eddy current.
First of all, what is iron loss? So whenever there is an electromagnet, the electromagnet will have a magnetism established because of the electricity. But if it is constant, then there is no iron loss. But if it is variable, then it is iron loss. I'll just explain what it is. So this is like not we are not solving any problem here. We are just uh, discussing some theory. So let's take a uh, piece of iron, and then we make a winding on that, and then here I send some DC current, let's say 2 amperes, and here we have, let's say, 1, 2, 3, 4, 5, 6 turns. Then we call 2 into 6 is 12 ampere turns, 1280. So I have given, what is this? This is called MMF, magnetomotive force. Okay. So we are sending a current in a coil which is wound across a iron material. So that is 12 ampere turns of magnetomotive force. That will establish a flux in the machine. Okay. So here the flux will be unidirectional. Uh, okay, since I'm recording, I want to be more accurate. If I was not recording, then I can simply. Okay, so I hope now you are getting the what you call the diagram. So this will come like this and then like this. So I'll make another example. Okay. So now you notice the difference between these two. So here the wire, in the blue one, the wire comes first and then goes behind and then like this. So whereas the winding there is reverse. Now the question is, what will be the direction of the flux? In this one, will the flux be upward direction, or so I'll take flux as upward direction or downward direction? Can someone answer this question? Will the flux be upward or downward in this? Downward? Okay. Some right hand rule or something. Okay. So let's see. Yeah. So I think it's downward only. So whereas here it will be upward because just it is opposite. Okay. Now, as long as the voltage is constant and the current is constant, the flux will not vary. Okay. What if I reverse these terminals? If I keep negative up and then positive down, then 2 amperes will come reverse, and then the flux direction changes. Okay. Magnetic flux. Okay. So, by the way, so if we are talking about electromagnet, right? So, where is the north pole and where is the south pole? See, now this became a magnet. So, because this became a magnet, the magnetic lines of flux will go from north pole to south pole outside the magnet. Inside, it will go from south to north. So, this is south and this is north. Okay. So, because here the flux lines will leave like this and then will go and then like this. So, whereas in this case, the north is up and south is down. So, if I keep an AC, alternating current, if I keep a AC voltage source, so the voltage source will be positive and negative. So, therefore, this current also will be alternating current. Okay, so this current also will be positive and negative, and therefore, the south will become north, north will become south, and keep changing. Okay. When the magnetic poles keep changing, what happens to the inside material of this particular magnet? So there is something called magnetic dipoles. Okay, so magnetic dipoles inside this, so they have to keep changing direction. So if your frequency is 50 hertz, that means what time period is 1 by 50, that is 20 milliseconds. So every 20 millisecond, north pole will become south pole become north pole, and keep alternating. Because of that, the dipoles will keep changing. Because of that, there will be something called magnetostriction. I don't know whether it is a separate word or two words. Okay, so this magnetostriction, that will generate heat. That will generate a heat. So that heat is called iron loss. But if you look at the working principle or construction of a DC machine, so this one is a electromagnet with DC. So there is no magnetostriction in the shunt field winding, but the armature actually rotates in the changing magnetic field. So in other words, if you see the, like, this is the pole, it's a two pole DC machine. So there is a north pole and south pole, and then there is this, magnetic fields. Inside that, the armature is rotating continuously. So because the armature is rotating, the core of the armature will experience reversal of magnetism. Because of that, iron loss will be there in the magnet. That will create heat. Okay, so heat, if it creates heat, what you have to do, you have to give a fan. Okay, so even if you see in your laptop, there will be a fan to cool the processor. Same way, there will be a fan in the motor also towards one end, so that will also add the mechanical losses, kind of thing. Okay, so finally, that is the story about this. Yeah, so I hope whatever I just discussed made some sense. Okay. See, if you keep going, the subject keeps on going. So it's up to us how much detail we want to go.
Sir, can you discuss one question on the rotational loss? Yes, sir. Rotational loss is same as this iron and mechanical.
No, no. Rotational loss will be, see, the iron loss is there, right? Yeah, actually, we call it. Yeah, I think we can see, unless there is a way to calculate the separately the magnetic iron loss, and you know like that, then because for the level of depth we are going in this course, because it's only a basic electrical engineering course, usually we count that also in the, see, these two, iron loss and mechanical loss together, we call it as a rotational loss. Okay, so for our purpose, we can consider that. We can actually again decompose this into two separate losses, uh, rotational losses and iron losses. So I think instead of that, we'll go to some other problem. Okay, so you mentioned that 4 5 problems are there, answers are not matching. Which one do you think is the most, what you call, the one which is not matching?
So for the same question of rotational
Yeah,
losses,
yes.
like my calculation for iron plus mechanical losses coming like somewhere in like kilowatts,
Okay.
and the options are in watts.
I think there was one other student who mailed me regarding that. So even that question is not correct.
Can you
I'll
try
take that
to
into
solve that?
account. What?
Can you try to solve that?
No, I think that why we'll take some other question, because that one I got a mail, and I answered one of the students with that. Just a minute. So So you're saying 3 and 4?
Yeah.
Okay. Anyway, so we'll just go to some other question paper and then we'll come out in the interest of time. Yeah. So your thing.
FN.
Huh? Sorry, I have to search here. Yeah.
FN.
FN,
PT.
PT.
ZW.
Yeah, I think I got. Which question in this?
Question number 9. So I'm getting 242.6767.
Okay, so looks like let's see. Let's quickly solve and see. I didn't see again. We are now addressing question number 9 here. So first step, draw the diagram. Okay, it will help you. So let's draw the diagram. So long shunt compound DC generator. Okay, so that is the thing. So let's go to a new. Okay, so long shunt compound DC generator. Okay, so again, from that we can have something like this. Sorry. So because it is a generator, the output will be electrical. So from the whatever I read, so this is the diagram. Okay, long shunt compound. Compound means there will be a series resistance also. So this is RSC, this is RSH, this is RA, and this is the load resistance RL. 380 amperes at 210 volt. Okay, so 380 210. 380 amperes at 210 volts. So assume this as 0 volts.
RE
Huh. So what are these values?
0.05.
Okay.
Series resistance 0.03.
Okay.
And shunt is 40.
What else is asked in the question?
EMF generator.
Huh. So what is the EMF generated? I think it is a straightforward question, right?
Yes.
So first thing is find the shunt current. So because it is a long shunt, there is no problem. Directly 210 divided by 40. Okay. So 210 volts divided by 40 ohms. How much is that? 4 5 is 20.
5.25.
5.25.
Yes.
So this will be 380 plus 5.25. Oh, sorry, that will be reverse direction because it's a generator. Upwards 385.25 amperes. Now we know this, the voltage drop we can find here. Okay, so 385.25. I think the brush contact drop also is
Yes, sir.
1 volt per brush. So there are two brushes. So I have to add 2 volts. Okay, so this is the drop, voltage drop. Okay, so how much is that?
32.8.
32.82 volts. So this one should be added to this 210. to get the generated voltage. Okay, so EG will be 242.82. So that's not in the options. Okay. So again, I'll make a note of it. But looks like what I calculated is the correct answer.
So one more question, sir.
Yeah, I think it's almost 11:54. Maybe there might be other class now. So what you do, you just whichever you really tried and then it's not matching, you let me know. What are the other questions?
So the same question means 13, 18, and 20. That is question 16.
I'll come back to it. So what you're saying?
13, 18, and 20.
So many. I thought this was all checked actually. See, I
Direct
for
formula question.
huh?
Like question based on direct formula as per your lecture, they are not giving the correct answer as per the option.
Okay, okay,
Like cross magnetizing and demagnetizing. Yes, sir. Sir,
Using the direct
in
formula.
my paper code, I had three such questions, sir, up till now.
okay, okay.